I am also recording this session using the OBS Studio, so you will have access to the recording once I upload it to you. So let us look at the meaning of this self-tuned pendulum neutralizer. So we are aware that whenever we are looking at the turning moment of the engine, right? So the turning moment of the engine is not constant, but it varies with time. So we can say that turning moment of an engine varies with time, right? And we know that the turning moment of an engine is dependent upon the type of engine we have. Either it is a two-stroke or the four-stroke, right? And we know that in the if you plot it, the stroke, you will get it like this, right? So on the x-axis we have the theta or omega t, and y-axis we will have the turning moment. So this could be the graph that we are going to get. Now in multi-cylinder engine, in multi-cylinder engines, the time period of variation of turning moment is depending upon the two factors. First is the variation or the rotational speed of the engine. You can say that it is dependent upon the omega, right? Correct. So the turning moment of an engine is depending upon what? Omega. And the second factor it depends upon is the number of cylinders. Okay. And the third factor is depending on the nature of the operating cycle. Nature of operating cycle. Now, what does this nature of operating cycle means? So, nature of operating cycle means essentially it is a either two stroke or a four stroke. Based on these factors, we know that this turning moment will depend upon these three factors. So, turning moment of a vehicle or engine is depending upon the three different things. One is the omega, that is the rotational speed of an engine. The number of cylinders, such as 1, 2, 4, 6, 8, 16, depends upon the type of engine, right? And what is the result of this? This dynamic turning moment will give rise to torsional oscillations. Okay. Gives rise to torsional oscillations of crankshaft. Okay. So what we are going to discuss? So we wanted to discuss how the pendulum type neutralizer can remain self-tuned at all rotational speeds of the engine and thereby control the torsional oscillations of the crankshaft. So for that, consider a pendulum with its support, rotating in a
Hello,
horizontal line.
sir.
Yes, bolo bolo.
Screen is not visible.
Screen is not visible. Everyone?
Sir, you shared the Jamboard, so I guess I'm looking at that Jamboard. We are not sharing a screen.
Can you see the Jamboard or not?
Yes, sir, it's visible.
I will reshare it probably, right? How many of you are not able to access the Jamboard? Acha. Screen is not visible. So, okay, 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 okay. Yeah. Now let me know if you are able to see. Hello?
Yes, sir, it's visible.
That's visible. Right. Okay, okay. So, uh, first discussion was related with the turning moment of an engine, and we discussed that turning moment of an engine varies like this, right? So, turning moment of an engine varies with the time period. Now, what happens in multi-cylinder engine? Multi-cylinder engine, the turning moment of an engine variation is depending upon the three factors. So, which are the three factors on which the turning moment depends upon? The first is rotational speed of an engine, that is omega. Second is the number of cylinders, that is 1, 2, 4, 6, 8, 16, and so on, depending upon the torque or the brake horsepower you require. And the third, depending upon the nature of operating cycles. So the nature of operating cycle could be either two stroke or four stroke, right? So we can say that this dynamic turning moment gives rise to the torsional oscillations of the crankshaft, right? And what we wanted to minimize the torsional oscillations. And because of this turning moment, what is going to happen? Torsional oscillations of the crankshaft is getting. And what we wanted to have the pendulum type neutralizer to be utilized in such a way that which can remain self-tuned to all the rotational speeds of an engine and thereby control the torsional oscillations of the crankshaft. Okay. So now let us consider the pendulum with its support rotating in a horizontal plane. Okay. Let us call this is the radius r. Let us call it is rotating with an angular velocity no. Right. Let us call the arm length is having the length L. Okay. This point is, let us call it as O dash, and it is able to rotate in the both the direction. This arm is able to sway in the both the direction. Okay. So this is a pendulum, pendulum with support rotating in a horizontal plane. Now let us first discuss what is the meaning of self-tuning. So in the self-tuning, the most dominant or primary exciting frequency, most dominant or primary exciting frequency is given by omega is equals to n into n0. This is for a two stroke. So what is this omega? Omega is the angular velocity, or we can say the excitation frequency, and it depends upon the n into n0, and it is applicable for the two stroke, whereas for the four stroke it will be given as n by 2 into n0, whereas n0 is the speed with which this engine will rotate. So it or the n0 is the rotational speed, and capital N is the number of cylinders. So n is the number of cylinders and n0 is the rotational speed. Rotational speed of an engine. Okay. Now let us look at the expression. So in this case, what we are doing, we are neglecting all the higher harmonics. All higher harmonics are neglected. So what is the meaning of neglecting all the higher harmonics? So the meaning is that all the higher natural frequencies that the object will possess, we are going to neglect. So take omega as the exciting frequency. All higher harmonics are neglected and take omega as the excitation frequency or exciting frequency. So the natural frequency of pendulum, we know that on which factor the natural frequency of pendulum depends upon, with length L, it is equals to under root of G by L, correct? Whereas L is the length of pendulum, correct? And G is acceleration due to gravity. Although you may be wondering where does that 1 upon 2 pi went? Yes, 1 upon 2 pi is also there, right? So this 1 upon 2 pi will give us the value is in the hertz. Okay, so this is the general formula I have written. Natural frequency of a pendulum will depend upon the under root of G by L. So if a pendulum moves in a horizontal plane with its hinge point O dash. Look at this. This is a pendulum which is moving in a horizontal plane, right? With its hinge point is O dash. Okay, hinge point O dash, figure 1. And at what speed it is rotating? Rotating at n0, right? And what is its radius? With the radius r, then the gravity field G is replaced by centrifugal field. Now what is the magnitude of the centrifugal field in this case? n0 square r. So it is very much similar to the formula of the centrifugal force that we have earlier studied, omega square r, right? So in this case, so natural frequency of this centrifugal pendulum can be obtained as omega n is equals to, now this g needs to be replaced. So we will replace the g by what? N square r, no square r, right? So we will write down this as, so this g will be no square r. So we will have now as the no square root, no will be outside. So we can write it down it as r by l and o, or we can also write it down like this, r by l raised to half into no. Okay, so this is the formula of omega and we are going to get for a centrifugal pendulum. Okay, now let us look at the next thing. Now let us take this case that if we attach this centrifugal pendulum, a centrifugal pendulum, if attached to the crankshaft, can always remain tuned to the exciting frequency. So we can write down the equations. So comparing equations, omega is equals to n into n0 and omega is equals to omega n is equals to r by l raised to half into n0. What we can get if we compare these two equations, right? What is the omega in this both the case? Omega is tuned, so we can say that this omega is same, right? So we can write it down, r by these two are equal, so n0 is equals to r by l raised to half into n0. So we'll compare these two. So we can write it down like this. Okay, so this n0 will get cancelled, right? And this we can take the square on both sides, so we will get n square is equals to r by l, right? Or we can also write it down like this, r by l is equals to n square, and this will be for the two stroke, right? And if we write it down the expression for four stroke, this is for two stroke. So we have for four stroke n by 2 into n0. Therefore, so this expression will become n by 2 into n0 equals to r by l raised to half into n0. Again here this will get cancelled out, right? So we will take the square. So what it will be, n by 2 square will be equals to r by l, right? Or we can also rearrange this term. So we can write it down, r by l is equals to n by 2 whole square. This is for 4 stroke. Okay, so these are the two equations we get. R by L is equals to N square and R by L is equals to N by 2 square, right? So these are the equations which will give us the necessary condition for self-tuning. Necessary condition for self-tuning. So whenever we are saying that the centrifugal pendulum is going to be self-tuning, it will follow this rule. That is R by L is equals to N square for 2 stroke, where R is the radius of the pendulum, L is the length of the pendulum, N is the number of cylinders for the 2 stroke, and for the 4 stroke, it will obey the relation R by L is equals to N by 2 whole square for a 4 stroke. Okay. Now let us look at the response of crankshaft with centrifugal pendulum. Response of crankshaft with centrifugal pendulum. For that, we consider the two diagrams. Point O, angle is in this case theta. This point is O dash. Let us call the pendulum attached here at a length of theta, and it is deflected by an angle phi. The torsional moment that is experienced, in this case let us call it as Tm plus To e raised to j omega t, that is the torsional pendulum turning moment. Then this is the I direction and this is the j direction. Let us call this point as A. Okay, and then let us draw the free body diagram in this case. This is the point O dash. This is the point A. Okay. And on this point O, the inertia force acting is M A I. That is by using the, we can say, D'Alembert's principle, or by using the Newton's second law of motion, we can write down what is the inertia force acting. And again, the inertia force acting on this mass A is neutralizing it. So we can say that the opposite inertia force will act on the point A. Okay. So this is a arm of a pendulum, right? And let us draw this pendulum without this centrifugal pendulum. Let us draw this torsional pendulum without the centrifugal pendulum. So this is a angular velocity. So this is the torque acting Tm plus To e raised to j omega t, right? This is the position O dash, O dash, and where the amount of the inertia force acting is M A I. Okay, so this is we are going to consider. So what is this? These figures indicate figure 2. This first figure indicates the, let us call this as A and let us call this as B, centrifugal pendulum. on a crankshaft, and the figure B indicates the free body diagrams of the pendulum and crankshaft. Okay. So what is the condition we have studied here? We know the conditions for self-tuning. I am rewriting down the conditions of the self-tuning again. R by L is equals to N square for 2-stroke, and R by L is equals to N by 2 square for a 4-stroke. So these are the conditions for self-tuning, right? Now these conditions can also be obtained by considering the motions of the crankshaft and the attached pendulum. So now consider the figure. What is given in the figure? Figure, uh, we can say 2A shows a pendulum of mass m and length L, right? What is the length L in this case? O dash A. Huh? So this length L is equals to O dash A. Okay. Now, where is the hinge point? For this pendulum, the hinge point is O dash, whose hinge point whose hinge point O dash is attached to the rotating crankshaft at a radius r. Okay. So we can say that there is a pendulum of mass m and length L whose hinge point is O dash is attached to the this rotating crankshaft at radius r. So what is the radius r? This O dash to O is the distance r. Okay. Now consider the angular velocity. The angular motion of the crankshaft is denoted by phi or theta. So let us call the angular motion of the crankshaft here, we denote it by using some angle denoted by theta. Okay. And let us call the motion of pendulum relative to crankshaft is indicated by phi. Okay, look at the figure. What we have called angular motion of the crankshaft is denoted by theta, and motion of pendulum relative to crankshaft is denoted by phi. Look at this. This motion of crankshaft is denoted by an angle theta, whereas the motion of pendulum related with this crankshaft is denoted by an angle phi. Okay. If you closely look at this figure, you will get this is theta, this is phi, and this phi is related with the pendulum, theta is related with the crankshaft. Now let us call the unit vectors. unit vectors along O dash A and perpendicular to it are represented as I and j respectively. So we can say that unit vector which is along the O dash A is I and perpendicular to it is j. Look at this. Along this is I and perpendicular to this is j. Okay. So along O dash A is I and perpendicular to O dash A is j. Now the turning moment of crankshaft is Tm plus T0 a raised to j omega t. Whereas what is Tm? Tm is the mean value which overcomes the load torque and generates a constant angular velocity m0, and this harmonic part causes torsional oscillations of crankshaft. Okay. Uh, So now let us write down the relative acceleration value in this case. So from simple plane kinematics, relative acceleration of point A with respect to O dash can be written it as, so we wanted to get what the acceleration of AO dash, so it can be obtained as I theta dot plus phi dot square to L plus J into theta double dot plus phi double dot into L. Let us call this expression as 4. Okay. Now it is beyond our scope that how do we get this expression? Then why do we get this theta dot plus phi dot square into L plus J into theta double dot plus phi double dot into L, right? We will have to do the complex mathematical approach for getting this expression. So we get the value of acceleration A dot O, that is acceleration of A with respect to O dash by using this relation. Okay, and here what we get, because the absolute motion of line O dash A is given by theta plus phi, so absolute acceleration can be obtained as, this is the expression for relative acceleration. So absolute acceleration of the point O dash with reference to fixed point O, right? Because we always obtain the absolute acceleration of any point with reference to the fixed point. So what is the fixed point in this case? In this case, the fixed point is O, right?
Yes, sir.
Yes. So we get the value of A, O dash as, again the expression we obtained is beyond our scope. I am writing down as it is r theta dot square. So r theta dot square is nothing but r omega square into cos phi minus r theta double dot. What do you mean by r theta double dot? R theta double dot means r alpha into sin phi, right? So this is the real part of the expression. Then I am writing down the imaginary part. So here r theta dot square, so which is again a r omega square. Here we have written first cos phi, then we will write it down as sin phi. Here we obtained the negative sign. The same expression we have to write down. Just plus sign we have to put. Then r theta double dot, and this sin phi will get replaced by cos phi. Right? So we write it down r omega square cos phi minus r theta double dot sin phi. Then we write down the same term r theta dot square, but instead of cos we write it down as sin phi, because once we rotate this unit vector by 90 degree, so the unit vector will now become in the direction of the sine if it is in the horizontal direction, and if it is rotated by 90 degree, then it will become cos if it is already in the perpendicular direction. So the same expression we have to multiply it by cos. Okay, so let us call this expression as phi. Okay, now by using the approach of vector addition, such as total acceleration AA is equals to acceleration of A with respect to O is equals to relative acceleration of A with respect to O dash plus absolute acceleration of A O dash A O dash O. Okay, I've written it here as same, meaning is same absolutely. Okay, so we get the total acceleration as this relative acceleration plus absolute acceleration, and from this if we add the jth component, what we are going to get? Let us add this to jth component. So we are going to add this to, okay. So let us find out what we get. We can simply add this theta double dot plus phi double dot to L plus r theta dot square into sin phi plus r theta double dot into cos phi. So we get that. So the jth component of jth component of AA as AA of j is equals to L into theta double dot plus phi double dot plus r theta dot square cos phi plus r theta double dot, wait, I have written wrong. There should be sin phi, r theta dot square sin phi plus r theta double dot into cos phi. This we get the j component of the acceleration. Okay, and this needs to be 0. This has to be 0 to get the free body diagram. To get free body diagram of pendulum as shown in figure 2b, right? Otherwise, what is going to happen? Otherwise, the moment of inertia force minus of ma j about o dash cannot be balanced. Look at this, the free body diagram. In the free body diagram, we can see only the two inertia forces acting. One is MAAI and another is MAAI, right? So both are balancing each other, right? And we can see there is no component of the this inertia force in perpendicular direction. So we can say that this j component which is in perpendicular direction to the A dash should be zero. Then only we can say that this MAA, that is the inertia force, will get balanced. Okay. So what we are going to do now, equate this to the zero. Okay. So so making AAJ equals to zero. So therefore we can write it down L into theta double dot plus phi double dot plus r theta dot square sin phi plus r theta double dot square, sorry, not double dot square, r theta double dot into cos phi. Okay, and this will be equals to 0. Okay, let us call this expression as 6. So this we have done it equated to the 0. And now what is the other expression remaining? Okay, that is the ith component. Now we will focus our attention to this ith component, this part and this part. Okay, the other equation of motion can be obtained from free body diagram. Free body diagram of crankshaft, that is figure 2b, right? Because we know with the known values of turning moment or moment of inertia, with the known values of its moment of inertia and the torsional stiffness. Now to revise what do you mean by the torsional stiffness, let us call this torsional pendulum having the disc like this. This is called as the length of this torsional pendulum, right? Right, and let us draw this top view. Yeah. Okay, so this is rotated by suppose angle theta. Now by using the equation of the torsion, we can say that T by J is equals to G theta by L. This equality we are taking, we are neglecting the equality tau by R. So by rearranging these terms, we are writing down the T by theta is equals to Gj by L. That is, theta is transferred here, J is transferred here, right? So what is the J, capital G here? It is the torsional, sorry, or we can say that the shear modulus. G is the shear modulus. J is the polar moment of inertia for this rod, right? And L is the length of this pendulum. So this T by theta is called as a torsional stiffness. Okay, and the unit of this is Newton meter per rad, because unit of torque is Newton meter and unit of theta is radians. So in this way we can obtain the torsional stiffness of any pendulum, torsional pendulum, of course, right? We should know what is this modulus of rigidity. We should know what is this polar moment of inertia. We should know what is the length of it, right? So in this case, what we can find out? We wanted to find out the values of the moment of inertia and the torsional stiffness. Okay, but we know that equation this 7, we call it as 6. Okay, let us call this as expression 7, and this expression we call it as 6. Okay? Equation 7 forms a set of non-linear differential equation. How we can say it is non-linear? Look at here. This is the theta double dot, right? So theta double dot means what? d2 theta by dt square, right? This is again a phi double dot. So it is d2 phi by dt square, correct? So this is theta dot square. So we can write it down as d theta by dt whole square into sine phi, right? This is r theta double dot. So it means r d2 theta by dt square into cos phi. So we can essentially see that it has a mixed proportion of the theta and phi. So we can say that this expression is non-linear equation because it doesn't have a single variable, but it involves the two variables. Correct? So it is a non-linear expression. So to avoid the non-linear expression, to avoid non-linear analysis, we assume crankshaft motion comprises of uniform motion. Now, what do you mean by the uniform motion? Having the constant angular velocity n0, right? So we are assuming that the crankshaft is having a angular velocity n0 superimposed with or superimposed on a small harmonic motion of amplitude mod theta dot and frequency omega. So what we have done in this case, to avoid the nonlinear analysis, we assume that the crankshaft motion consisting of only uniform motion, and to have the uniform motion, the angular velocity is considered here is n0, and this uniform motion is imposed on a small harmonic motion of the amplitude theta 0. So what we assume, a small amplitude of the motion for the pendulum is theta 0 bar. What we have to consider here, small angular displacement for the pendulum is theta 0 mod. Okay, so from this we can write it down. Thus, we can write it down expression as theta is equals to this n0t plus theta 0 mod into e raised to j omega. This is the first expression we get. Then we can differentiate this expression, differentiating with respect to t. So we can write it down this n0t as n0 plus this theta 0 will be constant, right? And e raised to j omega t differentiation is e raised to j omega t multiplied by the j omega. We can write it down j omega into theta 0 bar e raised to j omega t. Okay, and this can be abbreviated as n0 as omega into phi is very less than n0. So we can write it down this angular velocity theta dot. What is theta? Theta is the displacement, and we can get that theta dot as the angular velocity that we wanted to get as n0 plus j omega phi 0, or sorry, theta 0 into e raised to j omega t. So in this case, this omega is the angular velocity and theta 0 is the amplitude, that is the angular displacement. And we know that this theta 0 is very small because we are considering the small harmonic motion of the amplitude theta 0. So what is the meaning of this small harmonic motion of the amplitude theta 0? Very small angular displacement of the torsional pendulum. So in that case, this angular velocity multiplied by theta 0 will be very less than the n0, right? So that's why we have written the expression like this. Theta dot is equals to approximately equals to n0. Let us call this expression as 8 and this expression as 9. Now from equation 8 we get theta double dot by differentiating with respect to t. What we get? This will be 0, right? And here look at this. This theta 0 j omega will be constant. So will be multiplied by the e raised to j omega. Again the differentiation of j omega t as j omega into j omega. We know that j into j will be minus 1, right? Because I square is minus 1. So what we get here as minus omega square theta 0 e raised to j omega t. Okay, this is the expression we get. That is minus omega square theta 0 e raised to j omega t. Because j square is equals to minus 1. Okay, so let us call this expression as 10. Now we will substitute the value of this theta dot is equals to n0 in expression this 10. Sorry, both the expression theta dot is equals to n0 and theta double dot is equals to this in the expression 7. What is the expression 7? This expression. This expression we will put these values. Okay. So let us look at what we get. I rewrite down the expression here. L into this plus r theta dot square sine phi plus r theta double dot cos phi is equals to 0. This is the expression 7. Now what we wanted to do, we wanted to have the replacement of the theta dot as n0, which was the expression number 9, and theta double dot is equals to minus omega square theta 0 e raised to j omega t, which was the expression 10, into this 7, right? So substituting equation 9 and 10 in expression 7, right? So look at this. This theta dot will be replaced by this term, right? So L into minus theta 0 e raised to j omega t plus phi double dot, right? This theta dot square will be replaced by n0 square, so r into n0 square sin phi plus r into this theta double dot will get replaced by minus omega square theta 0 e raised to j omega t and into cos phi, and this equals to 0. Now we rearrange the terms, we add the terms involving the theta omega square theta 0 j omega t, we combine this, right? So what we get by combining these terms and combining the terms involving the phi, okay? Look, look at this expression is obtained now as phi double dot plus r by L into NO square phi equals to L plus R by L into omega square. This adds theta 0 bar and e raised to j omega t. So this is the expression we get, 11. So in this case, this sin phi and the cos phi are eliminated. In this case, this is sin phi and this cos phi is eliminated, and we have written down the expression like this. And how we have obtained? By substituting the values of these two terms. Okay. Now, assuming the solution is of steady state, assuming the steady state solution of form phi is equals to phi 0 e raised to j omega t, substituting this in equation 11, that is just now that we obtained in this expression. So what we are going to substitute? Phi is equals to phi 0 e raised to j omega t, right? So we obtain the expression as phi 0 by theta 0 by phi 0 mod is equals to r by L into NO square minus omega square divided by L plus R divided by L into omega square Let us call this expression as 13. Let us call this expression as 12. And thus for theta is equals to phi 0, that is when oscillations of the crankshaft are prevented. Are prevented when when R by L into NO square is equals to omega square, right? And using expression 1 such as R by L is equals to N square for 2 stroke, and R by L is equals to N by 2 square for 4 strokes. So these are identical with expression 3. Now what is the expression 3? These two are nothing but called as expression 3. This and this. Okay. So how we obtained? Let's revise. First we considered a self-tuned pendulum neutralizer, right? What is the condition? In a multi-cylinder engine, the turning moment varies with rotational speed of an engine, number of cylinders, nature of operating cycles. So we can say that the nature of operating cycle is depending upon whether it is a two-stroke or four-stroke, and we can say that the dynamic turning moment of a multi-cylinder engine varies or causes the torsional oscillations of the crankshaft. So what is our objective? To minimize the torsional oscillations of the crankshaft. For that, what we are using? We are using the pendulum type neutralizer. So this pendulum type neutralizer can remain unaffected or self-tuned at all rotational speeds of the engine and thereby control the torsional oscillations of the crankshaft. So what is the self-tuning? In this self-tuning, most dominant or primary excitation frequency is given by omega is equals to n0 and omega is equals to n by 2 n0 for 4 stroke. Whereas what is n? Capital N. In this case it is a number of cylinder, and what is n0? Rotational speed of an engine. So we consider the pendulum with a support rotating in a horizontal plane. So this is a pendulum with a support rotating in a horizontal plane, and this torsional pendulum is attached here, O dash to A. Okay. So for this, there is this centrifugal pendulum, if attached to the crankshaft, can always remain tuned to the exciting frequency. Right. So what we have considered? So for necessary conditions for self-tuning are, these are the two conditions for self-tuning. Omega is equals to n into n by 0 and omega n is equals to, or we can write, keep that omega n word, right? Writing down it closer. So this omega n is equals to r by l square n0. Whereas what is omega n? It's the natural frequency. So in this case, by rearranging the terms and comparing the expression, what we obtain, r by l is equals to n square and r by l is equals to n by 2 whole square. Right? Now we wanted to obtain the response of crankshaft with centrifugal pendulum. So for that we consider this crankshaft with a centrifugal pendulum attached at a distance a from the O dash is the point of suspension. So let us call the theta as the angular displacement of the crankshaft and phi as the angular displacement of the this torsional pendulum with respect to the line of action of this O dash, right? Where is the point O dash? O dash point is here. Okay, this is the point O dash. Okay, now the free body diagram is drawn here. So we have drawn the O dash to A, and what is the inertia force acting on this? Inertia force acting on it is MAAI, and this will be neutralized by the opposite inertia force MAAI, right? Whereas I indicates the unit vector along the direction, this direction, right? In which the force acts. Whereas for the crankshaft, it is only having the this turning moment Tm plus To e raised to j omega t, right? And this point O dash is having a MAAJ. Okay. So from this, we obtain the angular motion of the crankshaft, which is denoted by theta, and and the motion of the pendulum relative to crankshaft as phi. Considering the unit vectors I and j in direction OA as I and perpendicular to O dash A as j. So we got the turning moment of this crankshaft as Tm plus To e raised to j omega t, right? Then we obtain the relative acceleration of point A with respect to O dash. Then we obtain the angular acceleration, absolute acceleration of point O dash with respect to O. Then we obtain the acceleration of A with respect to O, which is the addition of the relative and absolute. Then we have separated out the jth component of the acceleration, which is this, right? And we know that this jth component acceleration should be 0, right? So we have equated this jth component of acceleration to 0, right? And thereby, what we obtained? We obtained the expression which is considering considerably nonlinear expression, right? So what we assume? We assume the crankshaft have a uniform motion, right? Having an angular velocity n0, right? And thus, by considering the small angular displacement theta 0, what we have obtained? Theta is equal to NOT plus theta O dot e raised to j omega t. By differentiating this, we expression we get it like this, and we know that this omega theta 0 is very small. So theta dot is obtained as n0, and theta double dot, by double differentiating this expression we get it like this. And then finally we substituted these values of theta dot and theta double dot in the expression 7. Okay. From this, what we obtained? We obtained this expression by rearranging the terms and eliminating the sin phi and cos phi. And to obtain the solution of that expression, what we assume? We assume the solution is of steady state, having the form phi is equals to phi 0 e raised to j omega t, and then by rearranging this and substituting this expression 12 in expression 11, we get this expression. So for we can write it down for theta is equals to 0 when oscillations of the crankshaft are prevented, when this is followed. That is R by L, NO square is equals to omega square. Okay. This is already shared to you. I will make a PDF and also share it to you.
Thank you, sir.
Okay. Now, somebody has asked a question. What do you mean by the hot damper or hot damper? Okay. So for that, we need to understand the self-Turing condition, or how does the effect of the counterweight in the centrifugal pendulum act. Understand that. Which is essentially called as auxiliary mass connected only by a damper. Now let us consider this case. Stiffness K1 connected to a mass M1, right? It is connected only to a damper. There is no spring, and then this is connected to a mass M2, right? Now let us consider the displacement of this mass M1 is x1, right? And as it is essentially a vector quantity, we are expressing it in the form of vectors e raised to j omega t, right? And this x is the displacement, so we write down also it is in the j omega t, right? Let us call this x2 is the displacement of the mass 2, so it is expressed it like this. Okay. Now, to understand the mathematical treatment of this, we need to first go through the other terms such as optimum tuning and deutering and centrifugal pendulums constructional features. Okay. So first we understand the optimum design of the damp absorbers. Then we will be able to understand the mathematical treatment given in the hot damper. Okay. So first go through the optimum design of the damp absorbers. So in this case, in case of the optimum design of the damp absorbers, it is applied to an undamped single degree of freedom system. So in this case, we follow the general principle of optimization when damper is present or damping is present in secondary system which is represented by complex stiffness, and then specific results for various types of damping, and then specific results for various types of damping. So let us consider what we are going to study here. It is fixed K1, this is M1, right? Then I have shown it this with a dotted line. There is specific reason behind it dotted line. I will tell you the reason. X1 is equals to X1 e raised to j omega t. So X1 is the displacement having the magnitude capital X1, and e raised to j omega t indicates the phase angle. X2 is the displacement of the mass 2, which is connected with the spring of K2 star, right? And X2 is the magnitude of the this mass 2. So in this case, the transmitted force to the foundation f of t e raised to j omega t, right? And F is equals to e raised to j omega. And how would the force act? Like this, like this. So force exerted is Ft, and force which is exerted on the mass M1 is F. Force exerted or force transmitted to this is Ft e raised to j omega t, and force exerted on the M1 is F j raised to omega t. Okay. So in this case, the first is called as force excitation. This is a case of force excitation. Okay. And now let us consider a case of base excitation. Right. So this is a K1 mass M1 having amplitude X1 X e raised to j omega t. Right. Then again this is K2. This is M2, and here X2 is equals to X2 bar e raised to j omega t. This is a case of base excitation, right? And both are what? These both are damped absorbers for an undamped primary system under harmonic. First force excitation and the second is base excitation. Now in this optimum design of the damped absorbers, what is in the first case we can see? In the first case we can see there is a undamped single degree of freedom system subjected to harmonic force, and in the second case we can see the base excitation. And in this case the solid lines in the figure A and B are shown, right? And these solid lines indicate the stiffness and the mass of the primary system, right? K1 is the stiffness of the primary system, and M1 is the mass of the primary system. And whereas the dashed lines are shown for the damped absorber, right? and this dash line indicates the mass M2 and the complex stiffness K2 star, so that the maximum value of the transmissibility is minimum in the entire frequency range from 0 to infinity. So what we obtain? So in this case, this T is equals to Ft by F for figure 3a, right? And this T is equals to x1 by x for figure 3b. Let us call this as equation 1, equation 2, right? And we can see that these both are identical. Both are identical. And we can say that transmissibility expression transmissibility expression in equation 1 represents response of primary system, since x1 is equals to ft by k1. We know this expression, and how do we know this? Because we know that force is equals to kx, right? So we can say that x is equals to f by k. So x1 is the displacement of the primary mass, and this x1 is the displacement of the primary mass will be dependent upon the force transmitted divided by the stiffness k1. Look at this figure, right? This x1 will be dependent upon what? Force transmitted ft divided by the stiffness k1. Okay. Now we will analyze only system in figure 3b, right? Now let us understand the design parameters. Design of damped absorber involves three parameters. First, mass M2. Second, stiffness represented by real part of K2 star. Now why we have mentioned the stiffness represented by real part of K2 star? Because it is mentioned that it is a complex stiffness. The K2 here is a complex stiffness we have considered. That's why the design of the damped absorber is only considered to have the real part of the K2 star. And the third point, in this case, the damping represented by imaginary part of K2 star. So the design of damped absorber involves the three parameters. First is the mass M2, second is the stiffness represented by a real part of K2 star, and the third is the damping represented by the imaginary part of K2 star. Now, in our analysis, first we define the non-dimensional mass ratio. Non-dimensional mass ratio, ratio लिखा मैंने, sorry, ratio M2 by M1. Let us call this M2 by M1 as mu, which defines the inertia parameter. Which defines the inertia parameter. Second, we define the stiffness parameter, which is described in terms of non-dimensional tuning ratio nu, such as what is nu? This nu is equals to omega by omega 0. And what is omega A? Omega A is equals to under root of K2A divided by M2. What is K2A? K2A is the stiffness of absorber at frequency omega A. And what is omega 0? It is equals to under root of K1 upon M1 plus M2. And this omega 0 is called as lock frequency, or also known as natural frequency of combined system when absorber mass is rigidly connected to M1. So these are the two important parameters. There are two more. Okay. The damping parameter we are need to discuss. The third parameter, damping parameter, is represented by non-dimensional loss factor. In the MCQ, you might have gone through this loss factor term, right? So we needed to know this term before we proceed. So non-dimensional loss factor, it is denoted by N2 omega, such that this N2 omega is equals to K2I star omega divided by K2R star omega. Whereas this I and R refer respectively to imaginary and real parts. Imaginary and real parts. So this N2, which is a depending upon the omega, is equals to K2I star divided by K2R star, and these both are depending upon the omega. Now the fourth factor, the forcing frequency. Forcing frequency is non-dimensionalized. Non-dimensionalized as excitation frequency ratio omega by omega 0, and which is denoted as omega. So we have the different four factors in our representation of the damped absorber design, right? Which are the four factors we are going to consider? first is non-dimensional mass ratio m2 by n1, which is omega, which defines what? Inertia parameter, right? So it defines a inertia parameter. The second that we are going to consider is stiffness parameter, and the stiffness parameter is considered in terms of non-dimensional tuning ratio, right? So what is this non-dimensional tuning ratio? Nu is equals to omega a by omega a by omega 0, because it's a ratio. So omega a by omega 0. Whereas what is omega a? Under root of K2a upon M2. Whereas what is K2a? It is the stiffness of absorber at the frequency omega a. And what is omega 0? It is K1 upon M1 plus M2 root. And this is called as lock frequency, or it is also called as natural frequency of the combined system when absorber mass is rigidly connected to the mass M1. So whenever the M2 is rigidly connected to the M1, so what we are going to get? We are going to get the increase in the natural frequency, decrease in the natural frequency, right? Because of the rigidly attaching this mass M2 to the M1. And the third parameter we are going to get is the damping parameter, which is a non-dimensional loss factor. So this N2 omega is equals to K2I star omega divided by K2R star omega. Whereas I and R refers to the real and imaginary parts, right? Or I and R refers to the imaginary and real parts. And the fourth is forcing frequency in a non-dimensionalized form as the excitation frequency ratio, that is omega by omega 0 is equals to omega, right? Okay. So we will continue our discussion later on. As far as the unit test is concerned,